Good morning, ladies and gentlemen. Thank you, Jim, for inviting me and for giving me an opportunity to speak here. And I will talk to you today about prospects for imaging habitable planets with a small space telescope. And let's see, do I have a clicker to advance the slides? This is the clicker? Okay. Let's make sure this works. There we go. Okay. So let me start my talk with this slide here, which shows an iconic image on the left of our Earth taken by the Voyager spacecraft from the edge of the solar system at the request of Carl Sagan about 25 years ago. It's a pale blue dot, a mote of dust suspended in a sunbeam, from the words of Carl Sagan. And what I'm trying to do, and the community of many exoplanet scientists, is to take an image like this of another Earth orbiting another star. And the image on the right here is a simulated image from a mission concept that we've developed showing a hypothetical Earth-like planet, another pale blue dot, orbiting Alpha Centauri. So let me show you some context. This is the night sky as it appears from New York. And every highlighted star in the sky there is a star around which we know that there's a planet. There are now close to 2,000 discovered exoplanets. And the number of exoplanets has been rising exponentially, kind of like Moore's law, doubling every 2 years or so. Most of the planets that have been discovered are similar to this one. They're not habitable. They are basically gas or ice giants. A handful of planets are potentially habitable, meaning they're roughly the right size and temperature for liquid water to exist on the surface, like this one, Kepler-186f. Now, there are only a handful of these planets that have been found, but it's not because they're not common. It's because they're challenging to detect. They're very small and therefore very challenging. In fact, the fact that we found any such planets at all means that they're ubiquitous in our galaxy. And as we zoom out, you can see that we've barely scratched the surface as far as searching our galaxy for planets. And most planets in our galaxy remain undetected, but we know that statistically there are more potentially habitable planets in our galaxy alone than people alive on Earth. As I said, most of them remain undetected, and in fact, technology doesn't exist quite yet to detect potentially habitable planets around the very nearest stars, such as Alpha Centauri, for example. We can detect potentially habitable planets in certain cases, but not in the general case. And but we're developing technology, and we're almost able to detect potentially habitable planets around the very nearest stars. And that's what I'll describe in the rest of my talk. The planets that I've shown you so far have mostly been detected by indirect means, and they give you limited information about the planets. So they give you planet size or mass. Oops, how do I go back? And an orbit, but they don't tell you anything about the composition of the planet or what gases might exist in the atmosphere. For that, we need either direct imaging or something called transit spectroscopy. But I'll talk to you about direct imaging, which is a fancy way of saying that you take a picture of the planet and then you take its spectrum. The main challenge with directly imaging a planet is that stars are billions of times brighter than planets. So the difference in brightness between our sun and an Earth-like planet is 10 billion. It's similar to trying to take a picture of a firefly buzzing around a lighthouse from about 10 miles away. And so the technology to do this is challenging, but we're getting there, and arguably we have it working in the lab already. This kind of technology is also already being used on ground-based telescopes. And here are images of planets that have already been imaged with ground-based telescopes. They're not potentially habitable. They're just the top of the cream of the very easiest planets. And let me tell you about one way of directly imaging planets. This is called an internal coronagraph. And this is a video produced by JPL. So the way that a coronagraph works is if you imagine light from a star entering a telescope, you have an image of a star that is very bright and it completely overwhelms the light from the planet. But you can use a series of masks and optics to block the star, and the planet misses the optics and it goes through, and you would be able to see the planet if you had perfect optics. But because you have imperfect optics, the image of a star looks like this. And you have to correct it by a device called a deformable mirror, which counteracts all the little imperfections in telescope optics and removes the starlight so you can start seeing the planets there. And I apologize, there's something wrong with the music track here, but it sounds ominous a little bit. It should sound inspirational, but so this video, by the way, is available online if you'd like to see it, as is the app that I use to produce the exoplanets in the galaxy in one of my first slides. So this is a roadmap of NASA's exoplanet missions. And the common wisdom is that it takes a large multi-billion-dollar telescope to directly image an Earth-like planet. And this common wisdom is correct, except for a few cases of nearby stars. In fact, you might be surprised to learn that to directly image a habitable planet around the nearest star system, Alpha Centauri, to us, a 30-centimeter telescope, which means a telescope with a 30-centimeter mirror, just about this big, is in principle sufficient to do that. And it could be much, much cheaper than some of these more expensive telescopes that are shown here, and could be launched potentially within a decade or even within 5 years. And so now these missions, in particular this, preview, particularly this New Worlds telescope, or it's known by many names in the 2030s, will be able to directly image hundreds of stars and search hundreds of stars for Earth-like exoplanets. But if you're willing to take a bet that Alpha Centauri has a potentially habitable planet, and there's actually a pretty decent chance, you could do it much sooner and much cheaper with a small telescope. Alpha Centauri, by the way, is a double star. So you might see a scene like this if there's a Earth-like planet around Alpha Centauri. And my team and I, and in particular my close friend and colleague Eduardo Bendek, we've developed a mission called ACET, Alpha Centauri Exoplanet Satellite, which is a 45-centimeter space telescope designed to be able to directly image pale blue dots if they exist in the Alpha Centauri system. Here is a data simulation from this mission. In the corner there, you see a sequence of images spanning 2 years of planets and noise from the star around Alpha Centauri. So you can see planets orbiting there amidst the noise. And if you process this data, you can get pretty high signal-to-noise detections of a Venus-like, Earth-like, and Mars-like planets in the system. So let me conclude with the following 3 points. Earth-like planet, or exo-Earth imaging, is within reach. Around the closest star system, Alpha Centauri, we could do it within a decade or even sooner. Or around other stars, we can do it within 2 decades. And a 30 to 45 centimeter high-contrast space telescope is, in principle, sufficient to directly image Earth-like and larger planets around Alpha Centauri. And my group, which is called the AIMS Coronagraph Experiment, is developing technologies and mission concepts to make this happen. And I'd like to leave you with this quote: "One day from the shores of a new world, we'll gaze at the sea that took us there, and its waves will be stars." You can imagine that centuries or thousands of years from now, when people stand on the shores of other Earths, they'd be looking back at our Earth and seeing a blue dot, and looking back at our time, knowing that it was our generation that found the planets that they're standing on. Thank you very much.